Hey everyone. Okay, let's take a look at lesson 7 of trig functions and graphs. So you guessed it, now that we know our basic trig functions, and I guess since you haven't done the assignment yet on lesson 6, you're probably not aware of what the cosine graph looks like. But the basic cosine graph looks very much like your sine graph in that it looks like this. Okay, so just to give you a heads up if you haven't done that assignment yet. And the sine graph, if you recall, the basic sine graph looks like this. They look very similar, don't they? But now what we're going to be looking at is basically what happens when we change the parameters a and b. Okay, now think back to transformations, okay? We're going to basically describe, using these different equations, what transformations have occurred to the original y equals sine x graph. Okay, so let's take a look at the first one. We have a 2 in front of our sine x. Okay, I think we seem to remember if we have a 2 in front of our whole function, that is a vertical stretch about the x-axis by a factor of 2. Okay, so it works normally when it's in front of the function. If it's over with the y, it's upside down and backwards. Okay, next one, we have a 2 in front of our x. So x was scooped out and replaced with 2x. Okay, so now we're dealing with x, so that would be a horizontal thing, or a horizontal stretch by a factor of, and this would be about the y-axis, by a factor of, this time we need to reciprocal r2 because it's with the x, so by a factor of 1/2. Good. Okay. Why don't you guys, oh, well, the next two have a slight complication with the negative sign, but the negative is not a stretch. That is so you wouldn't go vertical stretch by a factor of -3. That's not quite right. There's a vertical stretch by a factor of 3. I'm just going to abbreviate that this time. The negative, however, is a reflection. Okay. And if you recall, a negative in front of the whole function, that would cause y to go negative. And if y goes negative, we're reflecting over the x-axis. So that would be our reflection. Reflection over x-axis. Okay, good. And next one, sine of -3x. Again, the negative is its own transformation. So we would have, first of all, our stretch. Remember the order in which you talk about the transformations. Stretch, reflect, translate, sort it out. Okay, so 3 would be a horizontal stretch because it's in front of the x. It's with the x, so we have to flip that to get our horizontal stretch factor of 1/3. And again, the negative is a reflection. But this time it's in front of the x, so imagine if x goes negative, we're reflecting over the y-axis. Good. Okay, so in which of the above examples is there a change in amplitude compared to the graph of y equals sine x? So amplitude was half the total range. Half of total range. Now range is something vertical, right? So if we're going to affect amplitude, we need to be looking at something that affects the vertical characteristics. And that would be a vertical stretch, okay? So in which of the above examples, I guess that would happen wherever we had a vertical stretch. So it would be I and triple I. There we go. Okay, next one. In which of the above examples is there a change in period? Okay, so period is a horizontal thing. So if we have a horizontal stretch, that would probably change that. And that happens in the second one and also in the fourth example. Okay, complete the table using graphing calculator if necessary. Okay, so recall from the last lesson, y equals sine x. The amplitude, half of the total range, it went from -1 to 1 for the range. Half of that was 1. We had an amplitude of 1. Okay, so imagine here's your sine graph. Okay, this distance here is your amplitude, and that equals 1. Okay, the period, if you recall, the length of one cycle went from 0 to, are we in degrees? I guess we are, 360 degrees. Okay, or in radians, that would be 2 pi. So we can do both. I better not do the slash, it looks like it's dividing. Okay, 360 or 2 pi. What we'll do is we'll do the radians out here so it doesn't mess that up. Okay, so period in radians. Okay, so that would be 2 pi. All right, so if we have a vertical stretch by a factor of 2, that would affect our amplitude, and it should double it, right? So we would have an amplitude of 2. Period, would that affect things horizontally? No, it would not. So those are still the same. Okay, now this was a vertical, or sorry, not vertical, it's with x, so that was a horizontal stretch by a factor of 1/2. Will the amplitude change from the original then? No, still be 1. Period will change though. So it was, if we stretch by a factor of 1/2, our period would be half of what it was. So 1/2 of 360 would be 180, and half of 2 pi would be 1 pi. Okay, now let's take a look. -3 sine x. So that was a vertical stretch by a factor of 3 and a reflection over the x-axis. Now, will that change our amplitude? Let's think about that. If we reflect, sorry, that was kind of a weird graph. If we reflect sine x, which looks like this, over the x-axis, it would end up looking like this. Okay, so the reflection in itself didn't change half the total range. It would still be going from -1 to 1, or if we stretched it, -3 to 3. So the reflection does not affect your amplitude. Okay, we don't need to worry about that. Okay, but the vertical stretch by a factor of 3 does. That would change our amplitude to, you named it, 3. Okay, there's no horizontal transformation, so it would still be 360 and 2 pi. Okay, next one. We have that negative. Again, we've discovered that doesn't affect the period or the amplitude to have the negative. If we reflect over the x, things would just kind of look like this, wouldn't it? Okay, so we have the horizontal stretch by a factor of 1/3. Okay, so amplitude still 1. We didn't do anything vertically. Horizontal by 1/3, we'd go 360 times 1/3, which would equal 120 degrees. Or 2 pi times 1/3 would equal 2 pi over 3. Okay, why don't you guys fill in the next two for amplitude and period, and then see if you can take a stab at what the last one would be there. All right, pause your video. Let's do this. Okay, so the next one, vertical stretch by 5, would basically take the amplitude times 5. Horizontal stretch by 1/4, flip that 4, we'd go 360 times 1/4, which would give us 90. And for radians, pi over 2. Okay, next one, we should have 1/3 and 720, or 4 pi in radians. So to talk about this generally, essentially that A value seems to be our amplitude, but that if it was negative, it doesn't affect the amplitude. So what we're going to do is throw absolute values around the A. Like up here, when it was -3, the negative really didn't do anything to the amplitude, right? We want the absolute value of that A. Okay, now B, as you can see, like when B was 4, we basically ended up taking the period and dividing by that 4 to get the new period. Or when B was 2, we'd take that period, 360, and divide by 2 to get your new period of 180. So essentially what we're doing there is we're going 360 divided by our B value, or in radians, 2 pi divided by the B value. Okay, those are kind of important. You'll see them summarized on the next page. Okay, so would you expect similar effects on the graph of y equals a cos bx? So cos graph looks very similar, right? The cos graph was kind of like this. Same idea, same period, same amplitude. So yeah, it would have the same effects. All right, let's look at the next page. Okay, so above this, they just kind of summarized what we just talked about. And here's where they kind of put it in a table to summarize it. Amplitude is the absolute value of a, the coefficient in front of our function, okay, which you can find by taking your max minus your min from your graph and dividing by 2, right? There's your range, divide by 2. Okay, period, 360 over the absolute value of b. Again, the negative does not affect it. It causes a reflection. Or we can do it in radians, 2 pi over b. Tan x, we're not going to get into in 30-1 the transformations of tan x. So you can look at that for interest's sake, but normal period for tan was 180 rather than 360. So that's why you see the the equation change here. And amplitude, if you, well, you haven't done the lesson yet probably, but the amplitude tan graph looks very weird, looks like that. And there is no amplitude because it goes forever up and forever down, so we can't have half the total range. Okay, so on the next example, we're going to look at how to graph a trig function manually. Okay, and I will go through that. But you want to take a look at your max and your min points, basically, when you go to do that, and then adjust the period accordingly. So let's take a look at that on the next page. Okay, so it says consider the graph of y equals 4 cos 2x between 0 and 2 pi for x, and they actually scaled our axes and gave us a grid already, so that was nice of them. Okay, let's get our amplitude. Amplitude is going to be the absolute value of a, which equals, if we're using the equation, that would just be 4. So amplitude equals 4, period is going to be, it's a cos function, so we're going, and we're in radians. Check your domain here, right? That tells us we're in radian mode. So we would be using 2 pi divided by the absolute value of our b, which is going to be 2 pi over 2. Now we're not really going to have negative signs in front of our x, so we could probably just remember that as 2 pi over b. Simplify that, we would get pi. So there's our period. Okay, so period equals pi. All right, so sketch the graph on the grid. Okay, so we know our amplitude goes from -4 to 4, okay, so that's going to be where our max and min points are. We have a cos function, and the thing we know about the basic cos function is, and you can graph this on the calculator to check and make sure, but our peak is on the y-axis for a cos function. So that means we're going to start at a maximum. So we're going to put a point at our maximum of 4. Now, because our period is pi, we know that point, we're going to go through a full cycle, and we're going to come back to that point after pi amount of time. So at pi, we're going to put another point at 4. And then after another pi, so 2 pi, we'd be back up at 4 again. Okay, so that's how your period can help you graph this. In between those, we should be hitting our min values. So we have 1, 2, 3, 4, 5, 6 squares. So at 3 squares, we should be at our minimum of -4. All right, and again, between these two values, we should be at a minimum of -4. And then we can even get a little better, halfway between the top and the bottom, so 3 squares, so 1.5 squares, we should be halfway between those, so at 0. Okay, so fill in a couple more points there, just so we can get a little more accurate here. All right, that looks good. Now just remember, when you connect the dots, don't make V's, okay? This is not that kind of function. So we're going to do a little rounding at the top. Here's how I do that. I put my little rounding things at the top and bottom first, and then I try and go through the points after that. So now we can go through the points, head for that, and that way it doesn't look so much like V's, although this one's not exactly easy to draw. Okay, and there we go. Awesome, that looks great. Let's try example 3. Write the equation of a sine function having an amplitude of 2/3 and a period of pi over 6. Okay, so they're saying sine function, so we're going to be having y equals sine, and then possibly something in front of x. So we know the amplitude, we can put that in front of the whole sine function because amplitude is the absolute value of a. Okay, period though, that is not equal to our b value. What we're going to have to do is, let me just show you how this is derived. If period was 2 pi over b, let's see if we can isolate b, because that's what we need now for the equation. If we multiply both sides by b, okay, that gets rid of that, and then we would have b times the period equals 2 pi, and now we want b by itself, so divide both sides by the period. And you know what we get? B is equal to 2 pi over the period. So we can use that to help us find the b value when we have the equation. Okay, so it would be b equals 2 pi divided by pi over 6. Okay, and dividing by a fraction, same as multiplying by the reciprocal, so times 6 over pi. Pi's go, and we have 2 times 6, which is 12, so b is equal to 12. All right, put that in, and that would be our equation. This is basically y equals a sine bx. All right, good. Let's finish these up in part 2 of lesson 7. I'll see you there.